In this video, I wanted to go over what's maybe the most important technical or computational kind of technique advancement that makes pretty much all of deep learning possible, or modern deep learning possible, and that's the backpropagation method, algorithm, technique, whatever you want to call it. And I say it's important for pretty much all modern deep learning, mainly because the way that we can actually feasibly and practically train these very large, very deep neural networks is to use the backpropagation algorithm, but that's also coupled with something called automatic differentiation, which frameworks like PyTorch or TensorFlow or Keras provide to us, the end user. This video is going to be about the backpropagation algorithm itself, and I'll probably have a separate video on how to do automatic differentiation in PyTorch, getting our hands dirty with some code. And before we get to the actual backpropagation algorithm, we need to talk about how frameworks like PyTorch actually represent their computation or mathematical operations, and that's with something called a computational graph. So this is a graph in the discrete math sense, like a social network, and not a graph in the sense of plotting a mathematical function. And the important takeaway from this is that a graph is kind of this abstract mathematical representation or data structure. And the computational graph is actually uniquely suited to performing automatic differentiation, and especially reverse mode automatic differentiation, which is why most, if not all, deep learning frameworks internally represent their kind of operations or what needs to be done using a computational graph. And it might sound daunting combining kind of programming with abstract math concepts, but it's really a lot easier once you actually see a simple example. So here we have a function f of x and y equals 3x squared plus 2y. The whole thesis of the computational graph, or why it's advantageous, is that you can decompose this mathematical function into much simpler kind of component parts. And this is similar to what you learn in school when you're doing order of operations. So the first step to understanding the graph is that we have what's called nodes as well as edges connecting nodes. And nodes are kind of the objects or the things in the computational graph. These represent values, variables, mathematical operations, and the edges basically define the order, the structure, the relation between all these. So the edges correspond to which variables are inputs to which operations, as well as what the outputs are and where they go and what further nodes to pass them to. So this is basically saying variable x, we want to pass it as input to the square operation, which really corresponds to performing a square on the input, in this case x squared, and this is equal to q. So this q is just an intermediate variable that is going to be helpful when we actually get to the backpropagation algorithm, but internally frameworks optimize and highly optimize how these graphs are actually run and how they actually are computed and stored. The next bit here is just the multiply by 3 operation. So the inputs to our multiply node are both q and 3, and the way to read this is you basically apply the operation multiply to the inputs q and 3, and those equal the output, in this case u. And to do kind of the second half of our math equation here, we have y times 2 equals z, and finally we have z plus u equals f. So to just write this out more explicitly and kind of recap what this graph represents, this first x going into square corresponds to x squared equals q. Then we have a q times 3 equals u. On the bottom, we have y times 2 equals z. And finally, we have z plus u equals f here. So if we substitute all these in, u in this case is, call it 3q, z is 2y, and this still equals f. And then the last bit is to substitute q for x squared here. So we're left with 2y plus 3x squared equals f. And this is just kind of basic calculus and substituting things. So the computational graph, you can think of it as a kind of clever way to represent mathematical algebra and how to kind of compose these operations. Now, it's often said that the backpropagation algorithm is really just a kind of repeated application of the chain rule, if you remember the chain rule from calculus. So here we have the same computational graph, and the computational graph is kind of the core representation or data structure of how computation is basically laid out in a framework like PyTorch. But backpropagation is an algorithm of what to do with this graph, essentially. And here are kind of the two derivatives that we might be interested in. On the left here, we have the derivative of f, which is our output, with respect to x, which is one of our inputs. And then the second one is the same derivative of f with respect to y. So both of these really correspond to, if I change my inputs, how do my outputs change? And to compute these two derivatives, we essentially are going to apply the chain rule over our entire computational graph. And as you might have guessed, we do this backwards from the output to the inputs. So while backpropagation actually applies starting with the end and going to your inputs, or what sometimes you hear is called the leaf nodes, we're going to write these equations out kind of going forward, since I think it's a little bit easier to understand. So here's our first partial derivative we're interested in, the derivative of f with respect to x. And with one application of the chain rule, this can be broken down into the derivative of f with respect to q, which is our intermediate output, and the derivative of q with respect to x, where x is our input. And the really kind of awesome thing about these partial derivatives is that you can perform just normal algebra on these derivatives. You can treat them like normal variables or normal numbers. So we cancel out the dq's since we have it in the top and the bottom, and this just equals the left side df dx. And this type of algebra with derivatives is going to be somewhat useful when we start applying this chain rule over and over and over and over again. So going back to our graph here, we made it to call it q, and the next step in our graph is to compute these partial derivatives of u as a function of the derivatives from the previous step here with q. So here we have our derivative of f with respect to x, and we can apply the chain rule one more time here, and we essentially can break down in an identical way the partial derivative of f with respect to q is really just the partial derivative of f with respect to u times the partial derivative of u with respect to q. And again, we can cancel these out, and this algebra just comes out to what's on the left side here, derivative of f with respect to q here. And going back and doing even more substitution here, because remember, q is equal to x squared, so the derivative of q with respect to x is really just 2x. And if we substitute everything in, we now have this kind of long-running partial derivative, the derivative of f with respect to x. And now we substitute in our 2x here, as well as we substitute in our derivative of f with respect to q. So this is just df dq. So hopefully you can see and kind of extrapolate how we can compute the final derivative of this whole thing that we're interested in, this df dx in terms of all known quantities. And the reason it's called backpropagation is because we usually start at the end where we have a known derivative. The derivative of f with respect to f or itself is just 1, and we essentially propagate backwards these partial derivatives. Taking one step, we have the derivative of f with respect to u, and then the derivative of f with respect to q, and finally the derivative of f with respect to x. And it's an identical thing on the bottom with y. So with backpropagation, you have this concept of the forward pass, which is essentially running from your inputs all the way to your output, in this case f. And then you kind of analogously have the backwards pass, which is where you actually compute all these derivatives here. And the really kind of core insight of backpropagation with a computational graph is that each node really only needs to know how to compute its output. So this is the forward pass. Given a set of inputs, given the operation that a node represents, how do I compute my output? As well as how do we compute the derivatives for just this node? So these derivatives here aren't the kind of full chain of derivatives. All a node needs to know how to do is to compute its own derivative with respect to the edges coming into it. And hopefully with this kind of toy example of just a single function, the kind of workings of backpropagation are starting to make a little bit more sense. And the beauty of deep neural networks and deep learning is that kind of if you can prove something works locally, it can be extrapolated to a network on the whole. So as long as we understand backpropagation with these simple kind of functions and a simple computational graph, there's nothing in what we covered that makes it specific to this one function. So this kind of technique can be applied to the deepest computational graph for a very large neural network.